All right, ladies. Last time we left off talking about thermoregulation. So, whenever the whole theme of um, this unit is homeostasis and maintaining some sort of balance. Okay. So we talked about thermoregulation. Today we're going to talk about osmoregulation. Okay. So we're going to talk about how water is balanced, but not only water, but also like dissolved substances in water. So this is a nice little picture. What is it? Bottom left corner. Sweat gland. Okay. So you can see the sweat gland actually reaching the surface of the skin. We know what the sweat gland is for, right? Why do we need to sweat? Why do we need to sweat? Let out heat energy. Very good. So what if you were born with a condition where you don't have sweat glands? Then you got to be careful, right? You cannot overheat yourself because that could be very serious for you. So we know sweating is important, but it comes at a cost, right? What's the cost? Nothing's for free. What do you lose when you sweat? You lose water. And we're going to talk about water balance, but also the balance of substances in water, because now we're going to turn our attention to osmoregulation. Okay? And we're going to focus on us. We're going to focus on terrestrial vertebrates, but I first want to talk a little bit about animals that live in water, because we have a problem that's different than what they have, right? They live in water. So you would imagine for them, they don't really have a problem about finding water because they live in water, right? It's actually not true. We'll talk about this in a second. So let's talk about waste. Okay, so here is 3 different types of waste products. These are things that you make when you break down substances that have nitrogen, okay? Ammonia, urea, and uric acid. Uric acid is the least toxic. Ammonia is the most toxic. But you can see in this graph here that ammonia requires the most amount of water to get rid of because it's so toxic, you can't really accumulate a lot of it. You have to get rid of it as you make it. So you got to urinate a lot. Sorry, I shouldn't say pee a lot. You got to urinate a lot to get rid of the ammonia. Whereas uric acid is like a paste. So like when a bird leaves a present on your car, that's uric acid, okay? And it's not as toxic, and you don't need to lose as much water when you're making uric acid. We typically make urea, okay? So urea is kind of in the middle. So we need water to get rid of it. So when you look at like urine content, okay, urea would be a very important component. It's a waste product. Okay, and we're going to talk about how your body gets rid of waste. We'll talk about how your body reabsorbs water. Okay, so we know if we make waste, we got to get rid of it, right? But we know it comes at a cost, and the cost is we lose water, right? So let's imagine you're a freshwater fish. Okay, you eat stuff, you make urea, so you make ammonia. Okay, you make one of those waste products, ammonia. Okay, what's the problem here? Nothing really. I mean, you're living in water, so if you pee a lot of water out, you urinate a lot, you remove a lot of water, you don't really have a problem because what are you living in? Living in an environment full of what? Water. So you lose a lot of water, no problem. Drink a lot of water. Right? Terrestrial animals have a different problem because you're living on land. So if you lose a lot of water, the problem is you might be in an area where you might not find a lot of water. So that's a big difference between us. So terrestrial animal has to be more, you can't just produce urine at will, right? Because that will dehydrate you. So we got a different problem to worry about than a freshwater fish. Now, you guys remember your osmosis and diffusion? Just really two simple rules, okay? Diffusion is what? It's the movement of substances from a high concentration to a low concentration. And osmosis is the movement of water. Do you remember what it is? Okay, so we're going to keep it really simple. Osmosis is the movement of water from where there's obviously more water to less water, but it's also the movement of water to where there is more solute or more salt. Think of just more salt, okay? The salt is a solute. So imagine you're a freshwater fish. Okay, here's the thing. What's saltier, the fish or the water? What do you think is saltier, the fish or the water? Where's there more solutes? The fish or the water? Well, according to this picture here, it looks like we are seeing water gain. That's the wrong color. Okay. We're seeing water gain, which means that the fish must be saltier or have more solute. So water goes into the fish because osmosis says the water will move towards an area that was more solute. So the fish gains water just through osmosis. Okay. Furthermore, that means that this whole unit is about balance. So the more water you take in, the more you're going to need to get rid of. What's the problem with drinking too much water? I mean, is that really a bad thing? So what? So you urinate a lot. Or is it more than that? Can drinking too much water kill you? What do you think the answer to that question is? It actually is. Sorry, it actually is possible. There are stories of marathon runners running long marathons. I don't know how many stories there are, but I know of at least one, okay, where a person died from drinking too much water. You could actually calculate, I did it in grade 11 chemistry, what's called the LD50 of water, how much water you need to drink to kill you. Okay, and I can't remember the number, but it's quite a bit. It's quite a bit. Why would drinking too much water kill you, though? In chemistry, when you add water, you're adding water to do what? The word starts with a D. Dilute stuff, right? Problem is, if you add too much water, where does that water go? It goes in your bloodstream, right? And it dilutes your blood. And we'll talk about later on, so what? You dilute the blood. What's the big deal? It is a big deal, okay? Because it's all about balancing out certain chemicals in your blood, which we'll talk about later on. So diluting your blood could be fatal. So this fish has a problem. It gains water because of osmosis, but that's okay because it just basically gets rid of it through urine. A freshwater fish has the opposite. Saltwater fish has the opposite problem. Now, how many of you have ever drank water from the ocean? Yeah, I wouldn't recommend it. It's very salty. It's about 3%, which means 3 grams for every 100 mils of water. So it's very, very salty. You don't want to be drinking ocean water. In fact, you often watch these movies where people are sitting in the middle of the ocean and they have no water. And you're like, just drink the water. You're surrounded by water, right? You can't drink the ocean water or seawater. Why? Why can't you drink salt water? It's water. What's the big deal? Just drink the water. Why can't you drink salt water? Think about what we just talked about. Water goes to where there's more what? More solute, right? So salt water won't actually hydrate you. It will dehydrate you. It will actually literally pull water out of your body. Which is, if you're already dehydrated and you drink salt water and it pulls more water out of your body, what's that going to do? That could kill you. Okay? So a saltwater fish has the opposite problem. A saltwater fish will actually lose water to its environment. So what do you do if you lose water? You drink it. But what a saltwater fish has evolved the ability to do is drink the salt water and then remove the salt. We can't do that. So you can see here that they can take salt water and remove the salt. What is salt water minus salt? Water. Okay? So even though they lose water, they can drink the salt water, remove the salt, and replenish the amount of water that they lost through osmosis. Now, what is a whale? Is a whale a saltwater fish, or is it a mammal? It's a mammal. So, whales can't do this. They don't have this ability to drink salt water and remove the salt from the water. They don't have that ability because they're mammals. You can't do it. We're closely related to whales, so whales can't do it. So how do whales get water? It's an interesting question. How do whales get water? Because they can't do what this fish does. You ever think of that? It's an interesting question. They're surrounded by the ocean, and yet they can't drink the ocean water because it's too salty. And they're mammals, and if they drink the salt water, it will actually dehydrate them and kill them. So what do? How do they get their water? How do you get water? Jerusha, how do you get water? You drink it. Most of your water, I don't know what percent, I would imagine way over 90%, but not quite 100% of your water is consumed through drinking, right? But I said not all. Can you think of another way you get water? It's another way you can get water. By eating foods that contain water. So how does a whale get water? It eats food. It eats the things in the ocean that have figured out the way to remove the salt from the water. So by eating those animals, they're getting the water from the food that they eat. Yeah, interesting question. All right. So, but we're going to focus on not the balance of water and salt and solutes in fish. We're going to talk about mammals, okay? So we're going to talk about terrestrial animals, and we're going to focus on the kidneys, okay? Here's a nice little picture of the kidneys. So you can see here the kidney. Have you ever picked up kidney beans in the grocery store? Now you know why they're called kidney beans, because they look just like this. These two things are called the ureters, and this is the bladder. Okay, this is the bladder. All right, so we're going to focus on terrestrial animals. Okay, and these are just some things about ways of gaining or losing water. We know that we can gain water through drinking or eating food, and we know different ways we can lose water. Okay, so we're going to talk about basically how the kidneys work in balancing out water and solutes and things like sugar. Okay, that's what we're going to focus on. So the key organ here is we're going to look at is the mammal. All right, sorry, not the mammal, the kidney. So here's a nice little diagram. Okay, here are the kidneys. These two glands on top of the kidneys are the adrenal glands. We will look at them in the next chapter. So does anyone want to guess what the adrenal glands make as a hormone? Think of the name. Malika? Adrenaline. Yeah, very good. Adrenaline. Okay. So they make adrenaline. Excellent. Okay. Now, we'll look at basically the structure of the kidney first. So here is a nice little cross section of the kidney. One thing that you see right away is that it's full of blood vessels. And that makes sense. Remember we talked about form and function, the connection between what something does and what it looks like? Well, what's the job of the kidney? What does it cleanse? What does it purify? If you have an issue with your kidneys, you have to go on dialysis. So this machine purifies the blood, very good, for you. Okay? Which, by the way, is awful if you need to go through dialysis. you can see the kidneys are full of blood vessels because that's what they're going to do. They're going to purify the blood. So here's a picture of the kidneys. So this is the outer part of the kidney. Okay, the outer part is called the cortex, and the inner part is called the medulla. So there's an outer layer. You can see here. It's called the cortex. So this layer, yeah, the cortex. Whereas the inner layer is called the medulla. The orientation is actually pretty important when we talk about how the kidneys work. Okay. Now, the kidneys contain millions of these structural units. Okay. These structures. So right now we're looking at a little sliver of the kidney. This is the inner part, the medulla. This is the outer part, the cortex. And you will find millions of these structural units called nephrons. Okay. Basically, what a nephron is, it's just a twisted tube that leads eventually to the ureters and then into the bladder. Okay. So anything basically, and anything that your body does not want, it will end up going into your bladder, which means you're going to get rid of it. Okay. You can see that kind of looks like a little snake. All right. This looks like the mouth of the snake right over here. Okay, we'll talk about this in a second. This is these are blood vessels. So you can see that you have these twisted tubes, and you have these blood vessels that looks like they feed into the tubes. Okay. So here's information about the nephron. Okay. So it's right here. So here's kind of what it looks like. There's that twisted tube again. Okay. You can see that it's surrounded by blood vessels. Okay. Here is the entry into one of these nephrons. You can see it's right over here. Maybe I shouldn't use red because red kind of blends in with the other colors. But this is the entry right here. Okay. This entry point, well, you'll see in a second, is called the Bowmans capsule. Okay. So this is the entry point right over here. This is the exit point. All right. Here's a picture of the Bowmans capsule. Okay. So basically, this what you're seeing here, these are just capillaries. Okay. Now, what are capillaries or capillaries, depending on how you want to pronounce it? What are they? They're blood vessels, right? They're the thinnest blood vessels. And if you remember from grade 11, diffusion can only occur through capillaries because the other vessels, the veins and the arteries, are too thick. So what you're seeing here is basically, I need you to think of this, the capillaries here, as filter paper. Now in chemistry, you guys use filter paper, right? And the filter paper will allow some things to go through, but not everything, right? And we'll talk about that in a second. So this is a picture of the Bowmans capsule. So this, here are the capillaries, okay? This is that capsule. Now, this is the entry point into the nephron. So if anything gets through, it will enter those tubules. If it can't get through, then it stays in the blood vessels. Okay? So remember, think of this as filter paper. This is basically like filter paper. What do you call something in chemistry that can get through the filter paper? You know what it's called? It's got a name. It's called the, starts with an F, I, L. Yeah, very good. It's called a filtrate. Okay? So the substances that can get through are called the filtrate. Water, for instance, can get through. Okay? I have a list here of things that can get through. I believe it's here. Okay? So you can see these are some of the things that can get through, like water can get through, small solutes like glucose, amino acids, sodium, potassium. here's a here's a cross section of the same thing. So here's that Bowmans capsule. Here are the capillaries. Okay, it's like filter paper. Okay, so the stuff that gets through is called a filtrate. Whatever doesn't get through just stays in circulation. Okay, so like for example, red blood cells. We know that the blood contains red blood cells. Do you think that gets through? If it did get through, where would it end up? Because remember, if it goes into the tubules, there's a good chance it might end up in your bladder, which means you're going to urinate it out, right? If you see blood in your urine, now you're girls, right? Either it's because of your menstrual cycle, or you have an infection. But other than those two reasons, should you see blood? The answer is no. Blood should not be getting through into these nephrons, okay? Okay, so this is basically what happens. About 1.2 liters per minute of blood enters the kidneys, okay, to be filtered. 99% of the water that goes into the nephrons gets reabsorbed, right? If you didn't do that, well, if you did the math, you would need about 150 to 200 liters of water a day. Otherwise, that would, you would die. So most of the water that goes into the nephrons gets pulled back. All right? All right. So what we're going to do, and so here's a neat little picture of actually the Bowmans. They kind of look like little brains, but they're really just capillaries. Okay? Okay. Now, some terminology that is really important. So are we okay with the orientation? The outer part of the kidney is called the what? Cortex, and the inner part is called the medulla, okay? Just some termination. The word reabsorption versus secretion, okay? Reabsorption means to be pulled back. So if something gets reabsorbed, it gets pulled back out of the tubules. That means it goes into the tubule, but it gets pulled back. Because your body wants it. Your body wants to reabsorb it, which means you don't want to get rid of it. Secretion is the opposite. Secretion means it's going to go into the tubules, and it's going to go into urine formation, which means you want to get rid of it. Okay? So are we okay with that? So reabsorption means you want to pull it back in. You want to basically put it back into the bloodstream. Secretion means you want to get rid of it. Are we okay with? So there's four things you got to remember. Cortex versus medulla, and reabsorption versus secretion. Okay. Now, let's talk about how it works. All right? So what I'm going to do is I'm going to show you a picture of the nephron, but I'm going to show it to you not all twisted up like this, because this is quite confusing to look at. We're going to untwist it and make it look like this. Then I'll show you an animation, which will make it even easier to understand. Okay? So, here is that Bowmans capsule. Okay? Right here, you can see it. Okay? This, I said, acts like filter paper. So whatever can get through, we call it the filtrate. Now, the filtrate is going to circle or cycle its way through the tubule. Okay? And if it stays in the tubule, it's going to end up going into the collecting duct, which ends up going into your bladder, which means you're going to get rid of it. You're going to secrete it. Okay? It's going to be part of your urine. All right? The nephron is divided into little regions. Okay? So this little region here, this is called the proximal tubule. This is the distal tubule. This is the collecting duct. This is the descending limb. This is the ascending limb. Okay? I want to focus on these two. Descending versus ascending. What's the difference between the two? By looking at this chart. One has a very specific role, and the other one has the opposite. Not the opposite role, but a different role. So what's the role of the descending limb? So I'm looking at this picture. What do you see is happening here? What's coming out? Water. So that means the water is being reabsorbed. Okay? Remember, reabsorb means it's being pulled out of the tubule. Okay? So water is being reabsorbed in the descending limb. What's being reabsorbed in the ascending limb? The salt. Okay? Let's look at those two first. Why is that happening? Okay? How does it work? Now, I'm going to show you another picture, because you may have noticed in this picture, you notice the shading of this diagram. You notice how it gets darker as we go down this way. I don't know if you noticed that. There's a reason why they did this. Okay, the tubule sits in a solution. Okay, and that solution becomes more concentrated as you go from the cortex, the outer part, to the medulla. And as you work your way towards the center, it becomes even more concentrated. So that means if you were to measure the amount of salt and solute, it would increase as we go this way. And you could see it in this diagram. So this is the concentration in milliosmoles per liter. Don't worry about the unit, it's not important. The important part is this. The important part is, as we go this way, the outside environment becomes more concentrated. Okay? Or think of it as saltier. Alright? Now, that's important because you learn in grade 11, or I think it was in grade 11, or maybe grade 10, that water goes towards the side that has more what? More solute. Okay? It goes towards it. So if you were to draw, like, for example, a box and a membrane. Imagine that there's a membrane in the middle, okay? And we had water. So imagine we had water, okay? Oops. Oh, it didn't come out. Okay. So imagine we had like little water molecules, okay? But the thing is, not only did we have water molecules, but on the right side, we also had salt. So we had salt on the right side. Okay. Now the salt is on the right side, but not on the left side. Which way will the water move? It's always towards the, well, I shouldn't say always towards the salt, because there are other factors, but it will try to move towards the salt, okay? So this is how the nephron works. This side is permeable to water. Now what does permeable mean? So it's permeable to water. So it's permeable to water. This side is permeable to salt. Okay? What does permeable mean? That means it can what? It can go through. Impermeable means what? It can't. So here's how it works. And you're going to see it in the animation in a minute, okay? As the solute, so the solute is, the filtrate, not the solute, the filtrate. What's the filtrate is mostly water, but there's stuff in it. Okay? There's solutes in it. So the filtrate has a concentration. Okay? And you can see right now the concentration of the filtrate is about 300 milliosmoles per liter. Now here's the thing. As the filtrate runs down this way, the outside environment is always going to be what? More concentrated. Because as we go down, the outside environment is saltier, right? Well, if you follow the logic in this diagram, which way will the water move? Towards the environment that has more what? Solute, which happens to be on the outside. So as the filtrate runs down, it's going to encounter an outside environment that has more solute, so the water is going to come out. But here's the thing. What happens if you have a cup of water? Okay? And in my cup of water, I have water, but I also have solutes. Okay? And it has a specific concentration. What happens to the concentration if I lose the water, but I retain the exact same amount?
Mr. Berry?
Hold on a second. Sorry. Okay. What happens to the concentration if you remove the water, or remove some of the water, but retain the same amount of solute? What happens? What happens if the amount of water goes down? Guys, come on. Let's answer that question. It's pretty easy. Number of concentration is what? Number of moles over V. So what happens if V goes down? Concentration goes up. Right? If V goes down, then C goes up. So what happens to the filtrate? The filtrate, as it loses water, becomes more what? More concentrated. Right? Now here's the thing. As the filtrate turns and goes up, now you have the opposite thing. Because the filtrate now is very concentrated, the fusion says it's going to want to move to an area that's less concentrated. So as we go up, the environment becomes what? Less concentrated. Which means the stuff is going to want to diffuse out. So what's going on actually is one side reinforces the other side. As we go down the descending limb, the outside environment is more concentrated. That pulls the water out. But as the water comes out, the filtrate becomes more concentrated. So as the filtrate cycles back up, the solute, the salt, which is very concentrated, is going to want to diffuse out. So one side reinforces the other side. So let's take a look at an animation, okay? This is a really good one. And you can see it here. So let's take a look at how this works, okay? So this is the same thing, just that it's not, so this is the exact same diagram I showed you, just that this part was actually bent on a 90, okay? But here it's straight, okay? So here is your proximal tube. This is the descending limb. This is the ascending limb, okay? This is that distal tube, and this is that collecting duct, okay? So here, instead of using pink, they're using purple. Okay. So here's that, all the parts. Okay. So now we see the color shading. Again, the color shading is just an indication of the concentration of the outside environment. Okay. All right, so how does it work? We talked about as the filtrate runs down, it loses water because the outside environment is more concentrated. And that's what you're seeing here. So right now we pause it. So right now the filtrate is sitting at around 700 milliosmoles per liter of concentration. As this runs down, the next section will have a concentration that's higher, right? So the water is going to come out. Water comes out. You can see that. And it gets to the point where, you know, things are going to want to balance out. So you reach like an equilibrium. Okay? But now, the filtrate is really concentrated. And as we go this way, this side is permeable to the salt, but not to the water. So water can't come out, but the salt can. So watch what happens as we go the other way. Okay? Oops. Darn projector. Okay, as we come back out, you can see that the fusion says that the stuff, the sodium, is going to want to move from the sodium being one of the main ingredients of salt. It's going to want to move to an area that's less concentrated, which is the outside. Okay? Okay, so you can see that. But here's the thing. diffusion is going to want to what? Make sure that everything gets balanced out, right? So I want to show you something. Keep an eye on this. Right now, everything's balanced out, right? If you look at the concentration of sodium or salt on the inside and on the outside, in this area, it's what? It's the same. So watch. Same. But not here. So what's going on over here then? That can't be diffusion. What do you call it when you can move something against the concentration gradient? Think back to cellular respiration. When you built the proton gradient, was that by diffusion? Diffusion is how the proton gradient was converted into ATP, right? You had a high proton gradient on one side of the membrane and they diffused to the other side. But how did you get that proton gradient? How did you move everything to one side? What did you use? Sons of the P. Ends and umps. We use pumps. What kind of pumps? Proton pumps. So, whenever you see something like this, we know that this can't be diffusion. Because diffusion balances stuff out. This is some sort of a pump that's working, okay? This is active transport. We will talk about this pump in more detail next time, right? Monday, not tomorrow, because I'm not here, okay? But this is active transport going on. And then that should be, if you're well hydrated, that means you had enough water. That's the end of the story. Okay? That's it for you. Okay? Next time, we'll talk about what happens if you're dehydrated. Because you'll notice nothing else happened, right? That's it. Nothing else happened. Next time we'll talk about, well, what happens if you're dehydrated. So we'll leave with this. How do you know you're well hydrated in real life? You might get symptoms, right? One symptom you might notice is you have to urinate frequently. Also, the color of your urine is an important indicator. What should the color of urine be? What's it? Don't be embarrassed, girls, to answer this question. Should it be a dark yellow or a very light yellow? Yeah, the clearer probably the better. Okay? Because if it's really light, that means most of it will always be water. But the darker it is, that means the higher the concentration of the waste products like urea are in the urine, which means it's an indicator of that you're not probably as well hydrated as you should be. Okay? We'll talk about next time what happens if you're not well hydrated. All right, ladies? Okay, that's it.